In the study of strength of materials, the compressive strength is the capacity of a material or structure to withstand loads tending to reduce size. It can be measured by plotting applied force against deformation in a testing machine. Some material fracture at their compressive strength limit. Others deform irreversibly, so a given amount of deformation may be considered as the limit for compressive load. Compressive strength is a key value for design of structures. Compressive strength is often measured on a universal testing machine. These range from very small tabletop systems to ones with over 53 mn capacity. Measurements of compressive strength are affected by the specific test method and conditions of measurement. Compressive strengths are usually reported in relationship to a specific technical standard. Introduction. When a specimen of material is loaded in such a way that it extends, it is said to be in tension. On the other hand, if the material compresses and shortens, it is said to be in compression. On an atomic level, the molecules or atoms are forced apart when in tension, whereas in compression they are forced together. Since atoms in solids always try to find an equilibrium position and distance between other atoms, forces arise throughout the entire material which oppose both tension or compression. The phenomena prevailing on an atomic level are therefore similar. The strain is the relative change in length under applied stress. Positive strain characterizes an object under tension load which tends to lengthen it, and a compressive stress that shortens an object gives negative strain. Tension tends to pull small sideways deflections back into alignment, while compression tends to amplify such deflection into buckling. Compressive strength is measured on materials, components, and structures. By definition, the ultimate compressive strength of a material is that value of uniaxial compressive stress reached when the material fails completely. The compressive strength is usually obtained experimentally by means of a compressive test. The apparatus used for this experiment is the same as that used in a tensile test. However, rather than applying a uniaxial tensile load, a uniaxial compressive load is applied. As can be imagined, the specimen is shortened as well as spread laterally. A stress-strain curve is plotted by the instrument and would look similar to the following. The compressive strength of the material would correspond to the stress at the red point shown on the curve. In a compression test, there is a linear region where the material follows Hooke's law. Hence for this region where this time E refers to the Young's modulus for compression. In this region, the material deforms elastically and returns to its original length when the stress is removed. This linear region terminates at what is known as the yield point. Above this point the material behaves plastically and will not return to its original length once the load is removed. There is a difference between the engineering stress and the true stress. By its basic definition, the uniaxial stress is given by where F equals load applied, N, A equals area, M2, as stated, the area of the specimen varies on compression. In reality, therefore, the area is some function of the applied load, that is, A equals F. Indeed, stress is defined as the force divided by the area at the start of the experiment. This is known as the engineering stress and is defined by AO equals original specimen area, M2, correspondingly, the engineering strain would be defined by where L equals current specimen length, M, and LO equals original specimen length, M. The compressive strength would therefore correspond to the point on the engineering stress-strain curve defined by where F equals load applied just before crushing and L equals specimen length just before crushing. Deviation of engineering stress from true stress. In engineering design practice, professionals mostly rely on the engineering stress. In reality, the true stress is different from the engineering stress. Hence, calculating the compressive strength of a material from the given equations will not yield an accurate result. This is because the cross-sectional area AO changes and is some function of load A equals I, F. The difference in values may therefore be summarized as follows. On compression, the specimen will shorten. The material will tend to spread in the lateral direction and hence increase the cross-sectional area. In a compression test, the specimen is clamped at the edges. For this reason, a frictional force arises which will oppose the lateral spread. This means that work has to be done to oppose this frictional force, hence increasing the energy consumed during the process. This results in a slightly inaccurate value of stress which is obtained from the experiment. As a final note, it should be mentioned that the frictional force mentioned in the second point is not constant for the entire cross-section of the specimen. It varies from a minimum at the center to a maximum at the edges. Due to this, a phenomenon known as barreling occurs where the specimen attains a barrel shape. Comparison of compressive and tensile strengths. Concrete and ceramics typically have much higher compressive strengths than tensile strengths. Composite materials, such as glass fiber epoxy matrix composite, tend to have higher tensile strengths than compressive strengths. See also, compression, box compression test, deformation, Schmidt-Hammer, tensile strength, references. Mikhail P. Groover, Fundamentals of Modern Manufacturing, John Wiley & Sons, 2002 USA, ISBN 0-471-40051-3, Corlister W.D. Jr., Materials Science and Engineering An Introduction, John Wiley & Sons, 2003 USA, ISBN 0-471-22471-5.